What do we do? Okay. First of all, let me just go over some preview of coming events. And I will be grading that homework, and you'll get that back tomorrow, the one that you handed in last week. And then there will be another one, and then there's a homework number 5 that's due on Friday. And then one last one, that homework 6, that'll be due at the test. So the test is a week from Friday on Chapter 14. I have finished up a test review sheet. I haven't written up all the full solutions yet, but that will already a question. Yes, Jenna.
Do you already have that available? Can you send that out today?
Which one? Okay, now one thing you'll notice here about the take-home quiz, okay, is yes, right, right, because I thought the last time there was a lot of stuff due at the test, so I'm breaking that up. So the take-home quiz that I will be handing out isn't actually due until the 21st. There's a whole week of spring break in there. All right, and then I thought I just might as well make it due on Friday of that week that you come back from spring break, which is the 21st. So there's plenty of time to be doing the take-home quiz. All right, and then I will this weekend I will be posting the test review solutions. In addition, then I think I'd like to have, or I think we will have, an in-class quiz on Friday, and you can use your notes. So, on the topics that are included on the quiz are listed there on the board. I'm planning for probably a half an hour or so for you to take on taking the quiz. So partial derivative, total differential, equation of a tangent plane, if the surface is written like that. So there's 2 different ways of doing it. Z equals fxy, linearization, chain rule, implicit differentiation, directional derivative. So you can use your notes. You might want to just kind of be prepared to have those things, look at those in your notes just so that they're readily accessible to you. Yes? Can you use the homework that you've done? Well, sure, that's no problem. Yeah. No, I did just say that I'm going to be grading it tomorrow, and we'll be handing it back Friday. Okay. All right. Okay. So let's. We have 2 more sections to cover in Chapter 14, and both of these sections have to do with finding maximum or minimum values of a function of 2 variables, all right? So let's first look at 14.7, maximum and minimum values. Now, let's take a little walk down memory lane to Calc 1, all right? So in Calc 1, of course, you were just talking about functions of a single variable, fx, and let's just draw a little graph here. So, you know, we can have functions that go up and down like this, and here's a kind of a strange looking graph. So this is our graph of f of x. And notice here on this graph we have 3 different points, and so the graph then goes down like this and then goes down like this. We have 3 different points that can be considered local maximums or minimums. Remember, those are the points where they have values bigger than the immediately surrounding values. So right up here at the top of the hill, we have a local maximum. Here at the bottom of the hill, we have a local minimum. And then here at the top of looks like this alpine mountain here with a sharp corner, we also have a local maximum. Now, these things share something in common. First of all, what's the value of the derivative at that particular point? Right, the value is 0. So f prime is equal to 0. Now, what about that pointy area right here? What would be the value of the derivative there? Undefined, does not exist. So here we have f prime does not exist or undefined. Okay. So this is where, with functions of one variable, you're going to be finding these local maximum and minimums. So let me put something down here in writing then. Recall, if f of x has a local, and I'm going to start just putting max and min just to cut down on the writing I have to do, has a local max or min at, say, x equal x naught, then we have two possibilities here. The first derivative at x naught equals 0. Oops, wait a minute, hold on, what's going on? Oh, okay, Harry, you guys, I'm going to be sending the take-home quizzes. I email all this stuff to your the faculty people. You'll be getting I'll be emailing that stuff to them probably sometime this afternoon. All right. So that's all the things. Okay. In fact, for you guys I'm not sure if you folks at Eureka got that entire message that I typed, so let me just take a second here, oops, and copy that whole thing that I had typed earlier. Copy, paste. Okay, so I'm just copying and pasting everything that I had typed at the beginning. All right, okay, now, the first derivative equals 0, or it does not exist. Or f prime and x naught does not exist. Right. Now, the thing is, we have a name, remember we have a name for these points, and they're called critical points. So let me just remind you of this definition. A critical point is where either f prime equals 0 or f prime does not exist. Okay. So I can put those last two sentences together and say that if a function has a local maximum or minimum, then it will occur at a critical point. So if f of x has a local max or min, these occur at what are defined as critical points. Okay. Now, so that's for one variable. Now, we have a similar kind of result for functions of two variables. So let's look at fxy. Now, remember, for functions of two variables, we don't just have a single derivative. We have two separate partial derivatives. So we have this result, which is very similar to the first thing I had written down. If fxy has a local max or local minimum, min, at a point A, comma, B, and let's assume that the two partial derivatives exist, and let's assume fx and fy exist at AB, then if it has a local max or min, then the partial derivative with respect to x is going to equal 0 at that point, and the partial derivative with respect to y will also equal 0 at that point. Oops, what do we got here? Oh, 10 points. The class quiz will be 10 points. That's the question here. Okay. Now, we also have a similar definition then for what is considered a critical point for functions of two variables. So, definition, A comma B is called a critical point if the first partial derivative equals 0, fx at that point equals 0, and fy equals 0, or the first partial derivatives, either of them don't exist, or either fx, fy does not exist. Okay. Now, frankly, for the problems that we're having, the types of functions that we're looking at, we're not going to have this situation where the partial derivatives don't exist. Okay, so really, what we're focusing on here is that at a critical point, both of the two partial derivatives equal 0. Okay. All right. So therefore, we can then conclude, put these things together. Thus, if fxy, function of two variables, has a local max or min, then it occurs at critical points. Okay. All right, let me just show just this little diagram here of what these local maximums and minimums look like. So basically, we know that these surfaces, they just can be rounded, go all over the place. Right here, we have like a top of a smooth hill. We have a local maximum. Down here, we have a local minimum at the bottom, like the bottom of the valley, so to speak. This is actually an absolute minimum because this is actually the smallest value that the function has altogether. But it's also a local minimum too. So, and then this is an absolute maximum, but it's also a local maximum. So they're basically like the top of the hill, the bottom of the valley type of things as far as just thinking about them is concerned. All right. Now, there is something that can happen here. We can have a critical point, and yet we don't have either a local maximum or a local minimum. So let me put here caution. We can have a critical point where we have neither a local max or min. Okay. And let's just look at how we actually have this in functions of single variables. If you look, let's just take a side trip here for a moment to single variables, and let's look at f of x equal to x cubed. All right. Well, its first derivative is 3x squared, and so that's equal to 0 at x, when x is equal to 0. But if we look at a graph of what x cubed looks like, it coming down, I'm coming from the right side, then it kind of flattens out here for a second and then goes back down again. So this here, right here, that's a critical point because the first derivative equals 0, but that's neither a local, I'm used to saying relative, that's neither a local maximum or a local minimum. Okay, so we have these things with first one variable functions. All right, let me give an example here then of this phenomenon, and I'll give a name for it. So let's look at this example here, where fxy is equal to y squared minus x squared. All right. And the graph of this thing does an unusual thing at one of the points. Okay, let's find fx. So we're keeping, so y is treated as a constant, so fx is negative 2x. And let's find fy. X is treated as a constant, so fy is equal to 2y. And find out, well, where do these equal 0? Well, it's where x equals 0 and y equals 0. So for this function, 0, 0 is a critical point. Now the thing is, so we say, okay, I'm going to have a local maximum or a local minimum here. All right. Well, let's look at this. Let's travel on this surface, except for right now we're just traveling along the x-axis. So let's go along the x-axis. Now, if we're just traveling on the x-axis, that means that our y-coordinate is equal to 0. So y is equal to 0. Okay. So our function here, y is equal to 0. I can look at it like this: fx comma 0, just along this particular curve, and so that's going to be 0 squared minus x squared. So our function is looking like minus x squared if I'm just traveling there. Now, this thing, minus x squared, this thing gets from my critical point, because it's a negative square, it is negative on either side of that critical point. So if I'm traveling in that direction, my critical point looks like a local maximum. Okay, because it looks like the top of the hill. So our critical point, I'll put this in quotes, looks like a local maximum. But now let's travel along the y-axis, traveling to the origin. Now along the y-axis, that means all my x values are equal to 0. So my function then, I can look at my function as f0 comma y, because all the x's are 0. So that's going to be y squared minus 0 squared. So my function there looks like y squared along that road, particular road. Now y squared, it's going to look like 0, 0 is the bottom of the valley, and it's going to go up on either side of it. So therefore, on that road, our critical point looks like a local minimum. So our critical point now looks like a local minimum. All right. Okay, this phenomena is called a saddle point. Okay. And I've got a little picture here to show why it would be considered a saddle point, why we have that name. Okay, here's my saddle right here. Let's look at this function right here. Oh, I see we have some interesting little, I didn't insert the Chinese figures, the Chinese glyphs or whatever in there. All right. So we have this function. I don't know exactly what it is. It's probably very similar to what I just wrote up there. Here, this point right here. Notice this thing looks like a saddle that you put on a horse. That's why it's called a saddle point. And at this point here on our surface, if I'm just traveling this way, and I think that looks like the x-axis, traveling along the x-axis, it looks like we're at the bottom of the valley, a local minimum. But if I'm traversing it along the y-axis this way, it appears to be a local maximum. So that's where we have, a saddle point then is where we have the two partial derivatives equal 0, but we have neither a local maximum or a local minimum. Okay. So a saddle point is where both fx equals 0 and fy equals 0, but we don't have a local max or min. But we don't have a local max or min. Okay. Okay, are we okay kind of with the saddle points and that, and with this critical point business? Now I want to go back again to functions of one variable. So let's go back to just plain f of x. And let me draw a little graph here again. This one will be much simpler than the other one that we had. Okay, so this is our graph of f of x. And so we see that right down here at the bottom here, let's call this where x is equal to c, we certainly have a critical point because the derivative is 0. So f prime of c is equal to 0, and so that's, of course, c equals a critical point. Now let's look at either side of that point. On the left side of this point, if I were to calculate a value for the first derivative, would I be getting a positive or a negative value? Negative value, right. Anywhere along here, f prime is going to be less than 0. Because remember, the value is the slope of the tangent line. Any tangent line along here is a line sloping downward. And then, of course, right here, we have that f prime is exactly equal to 0. And then we go on the other side of the critical point, and our first derivative values are now going to be positive, bigger than 0. So let's look at what the first derivative is doing here. It's going from a negative value to 0 to a positive value. So therefore, on this particular curve, we can say that the first derivative is increasing in value. All right. Now, if the first derivative is increasing in value, what can I say then about its derivative, which is the second derivative? If a function is increasing in value, don't even think about this. If a function is increasing in value, is its first derivative positive or negative? Yes, it's positive because it's going up. Its tangent line will be up. So the derivative of the function we're talking about is f double prime, because f prime is the function that's increasing in value. So its derivative is f double prime, And so f double prime will be positive. Okay? All right. Okay. And we have a similar situation here. Let's then just kind of turn the curve upside down, where again here we have a critical point here. And in this case, so right here, of course, f prime of c is equal to 0. Now, however, yes, Jenna?
How do you know that it's increasing? Where's the function even at?
Where is the function even at? Okay. Now, you could go and graph f prime of x. In other words, if I had a specific function here, okay, I can get its derivative, and I can put its derivative on a graph. If it's a function, I can graph it. And I'm going to see that its graph goes up from lower left to upper right. So any tangent line is going to be positive in slope. So therefore, the derivative of my first derivative is going to be a positive value. I mean, I think when you say there isn't any function, see here we're talking abstractly. If you're looking at specific functions, there definitely is going to be a function there for the first derivative, all right? I don't know if that helped or not. Not really. I knew you'd say that. Okay. You can talk to me afterwards about it if you have a minute. Okay, now here on this side then, our first derivative is going to be positive because our graph is going upward. And on the other side, the graph is going downward again, so our first derivative is negative. So in this case, our first derivative is going from positive to 0 to negative. So therefore, our first derivative is decreasing in value. And if a function is decreasing in value, its derivative value, the value of its derivative is going to be negative, right? So therefore, f double prime is less than 0, right? So this leads up to, I don't know if you guys specifically remember the name of this. This in first semester calculus was called the second derivative test. That ring a bell?
Is that concavity?
Yes, right. Since Cassandra mentioned concavity here, this curve here, the first one I drew, is concave up. The second curve I drew here was concave down. Okay. Now let me just write down specifically what the second derivative test was. Second derivative test. Oh, before I do that, what do we have here? On our first graph, we have a local minimum. My second graph, it flipped around, we had a local maximum. Okay, so here's the second derivative test, and it says this. If C is a critical point, and f prime of c equals, so f prime of c, so therefore f prime of c equals 0, and if f double prime of c is greater than 0, then we have a local minimum. That was my first graph. Local minimum, our second derivative here was bigger than 0. All right, and then this other part of it is this. If f prime of c is equal to 0, so that means we're at a critical point. And now this time around, the second derivative, is less than 0. And that's the case with the second graph I drew. Then we have a local maximum at our critical point C. Now, I found that when I have taught survey calculus class, the textbook had a really nice diagram in it, which always caused some reaction from the class. So I do want to share it with you guys. That actually can help you remember the second derivative test. But sometimes this can get a little murky. So in a way, you can use these two faces to recall the second derivative test. Terry, I can have a little smirk there on the lip. All right. So the positive sign here means that the second derivative, that's the second derivative being positive. The negatives here mean the second derivative is negative. The mouth is the shape of the curve. So here, this is a concave down curve, and this is a concave up curve, all right? And then finally, if you think of this person as having a blemish or dare say a cold sore right in the middle of their mouth, right there, that tells you whether you have a local maximum or minimum. So with this one, if the second derivative is positive at a critical point, right here, you can just see it very visually, we have a local minimum. With this one, at a critical point where the second derivative is negative, you can tell right there, we have a local maximum, okay? So I don't take credit for this is something in a textbook by a gentleman named Bittinger. So anyway, that's just review, shall we say, for first functions of one variable. Now let's go back to functions of two variables. And we also have a second derivative test for functions of two variables. All right. Now, bear with me. Writing out this test takes a couple of minutes here, but we're then going to go through a couple of examples. Okay. So suppose the point A comma B is such that fx at A comma B is equal to 0, and fy at A comma B is also equal to 0, i.e. A comma B is what we call a critical point. All right. Now, what we have to look at here now is not as simple a calculation as with the function of one variable. What we have to calculate is the following. They give it the notation capital D. And this is what we have to calculate. fxx, so we do have to figure out the second partial derivative. fxx evaluated at this point times fyy evaluated at this point minus fxy evaluated at this point squared. So let me put nice asterisk by that formula. Okay. Now, so once we figure out this, then is a number. This is what we get after this calculation. So what does this number tell us? Well, if this D value is bigger than 0 and fxx at A comma B is also bigger than 0, then we're going to have a local min at AB. Now, way to remember this again is actually that little happy face drawing. We look at FD has to be positive. FXX has to be greater than 0. So that in that case, I'm looking at the face with both the plus signs for the I. FXX bigger than 0, and that shows me I have the local minimum. Now, if D again is bigger than 0, but this time around FXX is negative. So FXX at AB is negative, less than 0. We're going to then get a local max at AB. Oops. And again, okay, here FXX is negative. You can then look at it this way to help remember it, and that indicates a local maximum. Okay. Now, okay, these two cases both involve the D value being positive, greater than 0. If the D value is negative, less than 0, then we have the saddle point. Then AB is a saddle point. Okay. So far, we've covered D being bigger than 0, D being less than 0. If you have the case where the D value is exactly equal to 0, this test fails. It gives us no information. Okay. All right. Okay. I think we have time to get through this one example before we'll take a break. All right. So I'm actually doing the little bit easier example first, believe it or not. The problem with doing these is the following. We have to figure out where both fx and fy equals 0. So those are two equations, and they have two unknowns, x and y. Now, they're not necessarily at all just simple little linear equations. Okay, they can be quadratic or cubic equations. So we're trying then to solve, and sometimes that can be a little tricky, right? So let's look at this first example. So we're given our function fxy, and it's got a lot of terms in it. Here it is, y to the third plus 3x squared y minus 6x squared minus 6y squared plus 2. All right, there it is. Now, and of course we're asked to find, values of any local maximum or minimums, and also that goes right along with this territory is find any saddle points. Okay. So the first step then is to get the two first partial derivatives, because we have to find the critical points first. So step one is get the critical points. That means we have to solve fx equals 0 and fy equal to 0. Okay, so let's get fx. That means y is treated like a constant. So the first term will go to 0. The second term, y is a constant, we're going to get 3 times 2, 6xy. Third term is going to be minus 12x. And the last two terms will go to 0. Okay. And now let's get fy, where x is a constant. Now here then, our first term will become 3y squared. And remember, x is a constant, so this all sticks around here, but our y goes to a 1. So this is plus 3x squared. X is a constant, minus 6x squared goes to 0. Okay, minus 6y squared becomes minus 12y, and 2 goes to 0. Oh boy, okay. So we set both of these equal to 0. Okay. Now, I'm hoping that it makes sense that we start with the easier one, all right? Which would be which one? Fx. So let's look at fx equal to 0. So we have here 6xy minus 12x equals 0. All right. So you want to look at this and say, well, can I factor this thing? In other words, is there a greatest common factor to both of those terms that I can move to the left? Yeah, 6x I can factor out. So GCF, let's put that question mark, factor, a question mark, and the answer to those is yes. So let's move out the 6x, and what we're left with then is y minus 2. So solutions, so once we factor something, that's always nice. So therefore, if any solutions to this, we're going to have either 6x equals 0 or y minus 2 equals to 0. Just the two factors. Well, of course, if 6x equals 0, that means that x is equal to 0. Or, and y minus 2 equals 0 means y is equal to 2. So basically, this one then leaves us with two cases to proceed in. We know that we either have to have x equals 0 or y equal 2 in order to get fx equal to 0. Now let's go with those cases and now go to the second equation. All right? Now go to fy equals to 0. And let's first of all, let's plug in our first solution for x, which is 0. So A, plug in x equals 0, replace x with 0 in that second equation. Well, let's see. Our second equation is this, 3y squared plus 3x squared minus 12y equals to 0. All right, now, first of all, I'm going to plug in x equal to 0. So when I plug in x equal to 0, that middle term goes away. And so I'm left with something that doesn't look too awful, 3y squared minus 12y equals to 0. Again, is there GCF? Can I factor this thing? And thankfully, thank the Lord, there is. All right, 3y. So I can factor out a 3y, and I get a y minus 4. So, what are our two solutions that we get from this? We either get that y is equal to 0 or y is equal to 4. All right, so let me recap on here what we have found out so far. So therefore, thus, if x is equal to 0, which is what we plugged in, then y is equal to 0 or y is equal to 4. All right? So therefore, we have now found two critical points. We're not finished yet, but we've so far found two critical points. What would their xy values be?
0, 0, 0.
Yeah, 0, 0, that's for x equals 0 and y equals 0, and 0, comma 4, x equals 0, y equals 4. Both of those, yes?
Question. So from the first equation we found x equals 0 and y equals 2.
Yes.
Now do we use x equals 0 could we use y equals 2?
Yeah, we're doing that next. Yeah. You're leading right into my next step. Because those two critical points are not the only two. Now we're going to go back, and part B here is we're going to plug in y equals 2 into our Fy. So part B, now plug in 2 for y in Fy equal to 0. Okay? All right, so let's see. Fy here was 3y squared plus 3x squared minus 12y. So every place there's a y, I want to plug in a 2. So that gives me 3 times 2 squared plus 3x squared minus 12 times 2 equal to 0. And that's looking like it's going to come out pretty nice. This is 12 plus 3x squared minus 24 equals to 0. So let's get all the numbers on the other side, and I'm going to have 3x squared is equal to 12. And this is looking even nicer because I'm going to have nice whole numbers as my result. So therefore, x squared is equal to 4. So therefore, when I do the square root, x either is plus 2 or minus 2. So now I have found 2 more critical points. Oops. Okay, now don't get your x's and y's confused. This is y is 2 and x is either plus or minus 2. So this is 2 comma 2 and minus 2 comma 2, my other 2 critical points. So now we have 4 critical points altogether. All right. Okay, and so this is all just the first part of this thing, is just finding the critical points. So, and this is not, this is as a whole, this problem is not a bad, shall we say, a bad problem for this. Okay. Now, what we now have to do for each critical point, we now have to calculate that d value. All right. So remember what the formula is for d. d is fxx times fyy minus fxy squared. So I obviously need to get fxx, fyy, and fxy. Okay. And those aren't too bad here. Okay, let's get fxx. So first of all, here is, earlier we had found that fx was 6xy minus 12x. So now we do its derivative again with respect to x. Therefore, we're treating y like a constant. So what am I going to get here? I think I'm going to get 6y minus 12, aren't I? Because the x is going to go to a 1. So that's my fxx. Let's now get my fyy. So here was my fy. So I'm again doing the derivative with respect to y. So what do we have? 6y. That goes to 0, and that's minus 12. So it's purely coincidental that they're both the same. So don't be thinking that they're both going to be the same. All right. We also need to get fxy. So we need to start with our fx and do its derivative with respect to y. So that means we're going to be treating x like a constant. Okay? X is constant. So we're doing the fx derivative with respect to y. X is constant. So I think my first term is going to become what? Right, 6x. The y is going to go to a 1. And then my second term will go to 0. Okay, so that's my fxy. All right, so I found those 3 things. Now this is what I recommend that you do here for calculating the d value. I recommend that you you do one critical point at a time, and initially, as your first step, just get the number values for fxx, fyy, and fxy for each critical point. Rather than taking this whole thing and foiling it out or doing all that crazy stuff, it's just easier just to get the number value of each one for each critical point. So we had 4 of these. So we had 4 critical points. So let's first of all look at the 0, 0 point. Now here's my formulas for fxx for the second partial derivatives. So when x and y both equal 0, my fxx is going to be what? 6 times 0 minus 12, so it's negative 12. My fyy is going to be the same thing. 6 times 0 minus 12, negative 12. My fxy is 6 times x, so that's 6 times 0, so it equals 0. Now calculate d. And it's going to be fxx, which is minus 12, fyy minus 12, minus fxy squared, minus 0 squared. So minus 12 times minus 12 is 144. So first of all, we know that the d value is bigger than 0. Now, where do we go from there? Well, let me put back here the original test. If our d value is bigger than 0, what we have to look at next is what is the number value for fxx. If it's positive, we have a minimum. If it's negative, we have a maximum. So here, what did we get for fxx? So look at fxx value, and we got that it equals negative 12. So it's a negative value. If you like, you can draw your little face here, and you can tell from the face, negative face, we have right up here, we have a local max at that first critical point, 0, 0. All right. Okay, let's plow through the other 3 critical points, and then we'll take a break. Now let's see, our next critical point that we found was 0, 4. So now look at 0, 4, and plug these in to our fxx and y and all that. Okay, so fxx is 6y minus 12, so this will be 6 times 4 minus 12. That's going to be equal to 12. fyy was also 6y minus 12, so that's 6 times 4 minus 12. That's also equal to 12. And then fxy was 6 times x, but x is 0, so that's 6 times 0. This is 0. All right. Then we calculate our d. We have 12 times 12, fxx, fyy, minus 0 squared. So again, we get a positive value for the d. So our next thing, though, is to look at the fxx value. And this time around, our fxx value is 12. It's bigger than 0. So I'm so used to doing this from the many semesters I've taught this that it's like I cannot not do it. So therefore we have the positive face, and therefore this tells us right here we have a local min at 0, 4. All right? Okay, we shall make it through this problem. 2 more critical points. Actually, they're going to end up, let's see, what are the other 2? Where did I put that? Oh, yeah. So the other 2 critical points was 2, 2. Let's look at 2, 2. All right? And so let's again look at the fxx value. And so we're going to plug in, this time we're plugging in 2 for y. So we have 6 times 2 minus 12, and we get a 0. So you may be able to guess what we're going to get. Let's do the same thing for fy. Y, of course, that is also 6y minus 12. 6 times 2 minus 12, we also get a 0. Now the fxy was 6 times x, that's 6 times 2, that equals 12. So our d value is going to be 0 times 0 minus 12 squared, and that comes out to be negative 144. We can stop for this one right here. It's less than 0 d value. It's a saddle point. No need to go any further with this critical point. So we have a saddle point at 2, 2. All right. Then let's look finally at the last one, which is minus 2 comma 2. And we're going to again get a saddle point for this one. Okay. fxx, I have 6y minus 12. That's again going to be 6 times 2 minus 12, which is 0. fyy is again going to be 6 times 2 minus 12, which is 0. And then fxy is 6x. Now that's going to be 6 times minus 2, which is negative 12. All right. D again is going to be 0 times 0, fxx, fyy, minus, now be careful here, minus squaring negative 12. Well, that's going to be equals minus 144. So again, we can stop right there for that critical point. D is negative, so we have a saddle point at minus 2, 2. Now, on a test, I'm just going to stop there as far as just identifying which of the critical points is a local minimum or a local maximum. However, on a couple of the homework problems, what they also want you to do for anything that's a local minimum or maximum, they want you to plug that xy into the original function to get the actual function value. So in this case, we found out we had a local maximum at 0, 0. So local max at 0, 0, we plug into the original function. And let's see, I don't even, where in the world, here's our original function. In this case, everything's going to be 0, and it comes out to be 2. So this is a local max value. What is it? Oh, thanks. I just rotated the screen. Wonderful. What am I doing now? Okay. Wonder. I don't know. I hate to stop. Oh, wait. Oh, here's the rotate button. How's that? There we go. Okay, so our local maximum value at that critical point is 2, and then the other one was what? 0, 4, we had a local minimum, local min at 0, 4. Again, when we plug this into the original, I wonder, did I actually do this on my paper? Let me just check and see. Okay. All right. I didn't actually do it, and I don't feel like doing it right now. So therefore, we have to plug in x and y. I need a break also. We plug in 0 and 4 back into our original function, and we get a number value. Is that all right? Let me get away with that. I hope you say yes, but I'm going to. Let's take a 5-minute break then.
Friday.
Oh, that's right, you had mentioned that before,
Uh,
yes, okay. Oh, yeah.
I know I heard he didn't make it.
Oh, I'm sure we can work something out, yeah.
Okay.
What I'll probably just do is just, maybe just give it to, well, wait a minute. Writing copies. Yeah. I made copies this morning. Yeah, just work on it, and then I'll just hand it to me.
Okay, right now?
Oh, okay, Monday.
Okay.
Yeah. Eureka people, are they just only having one of you sign in now, because of the bandwidth problems that we had had? This is a test to see whether anybody's there. Okay. No response so far. I hope they're paying attention. let's do another example of this thing. So this one, again, the function here is x to the fourth plus y to the fourth minus 4xy plus 1. And so the first thing we have to get are the critical points. So let's get fx. And so y is a constant, so we're going to have 4x to the third. That's going to be 0. Y is a constant. That's going to be minus 4y. Fy, x is a constant, so we're going to get 4y to the third. Now x is a constant, minus 4x. Okay. So here we have it. We have two different equations here. 4x third minus 4y equals 0. 4y to the third minus 4x is equal to 0. Okay, so let's look and see what these both give us. Now, if I add 4y to both sides here, I get 4x to the third equals 4y. And, of course, I can divide by 4, so I get x to the third is equal to y. And then for this other one, if I add, I get 4y to the third is equal to 4x. And if I divide by 4, I get y to the third is equal to x. So these are the x to the third equal y, and then conversely, y to the third has to equal x. All right, so these are the constraints that have to be satisfied here. Now, basically, of course, you could kind of look at this for a minute and then think of possible solutions, but I'm going to do it a little bit more formally. So here, this is equation number 1. This is equation number 2. So what I'm going to do here is just take, okay, first equation tells us that y has to equal x to the third. So I'm going to go to my second equation and plug in x to the third for y in my second equation. Does that make sense? I'm basically using substitution method to solve two equations. Okay, you have, if in one equation you have a variable equals something, you can plug that into the second equation, substitution. So I'm going to plug in x to the third for y in this second equation, number 2. So that gives me, now y to the third then is going to become x to the third, that's my y, but I have to raise that to the third power, and that's going to equal x. Now, x to the third raised to the third power, we multiply the exponents, so that's x to the 9th equals x. Well, to solve this, let's just get 0 on one side, and we can do a little bit of factoring, all right? So let's get 0 on one side, so we'll subtract x, so we have x to the 9th minus x equal to 0. Now, we do see that, yes, we do have a common factor, so I can do some initial factoring of this. We have a GCF equal to x. So let's factor that out, and so x to the 9th now becomes x to the 8th, minus x becomes minus 1. Now, this right here, x to the 8th minus 1, well, for one thing, it is the difference of 2 cubes, but I don't know if everybody just has that formula on the tip of their tongue. But it's also the difference of 2 squares. 8 is 4 and 4, 2 squares. And we all have that formula. So I want to factor it further. So x to the 8th minus 1, I can factor as x to the 4th plus 1, x to the 4th minus 1, difference of 2 squares. And this all equals 0. And then we look further. Now, I cannot factor x to the 4th plus 1 with real numbers. But this, again, is another difference of 2 squares. So let's factor further. So now we have x times x to the 4th plus 1. Now this is going to be x squared plus 1, x squared minus 1. So we're able to factor further, and now let's stop there with the factoring. That's good enough. There's not going to be any solutions here in the real numbers for these two factors to equal 0, because they're both x to the 4th plus 1 equals 0. We're not going to get a real number solution for that, nor for x squared plus 1. But I've got these here. We can set x, that first factor equal to 0, and that other factor, x squared minus 1 equal to 0. And that's going to give us 3 values. Are you clear on why I can't do anything with the 2 middle factors? Because that's going to involve I, the complex numbers. All right. So we have one value here, x must equal 0. And now this is easy. X squared is equal to 1. So therefore, do the square root, x has to be plus or minus 1. So by doing all that, we have that x has to equal one of three of these values. All right? Okay. So now what happens? So x equals 0. Now let's see, what's going to be our y value if x is equal to 0? Here's our 2 equations that have to be satisfied. So if x is equal to 0, what must y be equal to? Yeah, 0. Okay, so 0, 0 is a critical point. So here I'll start listing my critical points. Now, the other thing we found, x could equal positive 1. So let's go back up here. If x is equal to 1, what value must y have?
Which equation are we plugging in? Which equation are we plugging in?
Okay, where I'm going from here is, remember we had done a little algebra and we came up with these 2 sets of equations that have to be satisfied for our critical points. These are the ones that I'm looking at. So when x is 0, 0 to the 3rd, y is 0. Now when x is 1, 1 to the 3rd power, y is going to be 1. All right? So that's our second critical point, is 1 comma 1. And then now a third value that x can be is negative 1. Now when we plug negative 1 into, say, this first equation here, we're going to get y has to be negative 1. So these are the 3 critical points, 0, 0, 1, 1, and minus 1, minus 1, that satisfy our 2 equations. All right. So now we have to do this d-test. So let's calculate our second partial derivative. Let's get fxx. Let me write up here what fx is so that we have it. Fx is equal to 4x to the 3rd minus 4y. Fy was 4y to the 3rd minus 4x. All right. Okay. So fxx, when we do the derivative, whoa. Oh. Okay. No, Jerry, I was asking about Eureka. Because but I never got an answer from them. Okay, fxx here, well, let's see, we do the derivative again of fx with respect to x, we're going to get what? 12x squared. Fyy, take fy, do its derivative with respect to y again, and we'll get 12y squared. And then fxy, start with fx, do the derivative with respect to y, which means x is treated as a constant. So I think we're just going to get negative 4. This is all going to go to 0, and the y will go to 1. Right? Okay. Now let's then look at each of our 3 individual critical points. Let's start at 0, 0, and find out what we get here. We get that fxx is equal to 12 times 0 squared, so it's equal to 0. Fyy is 12 times 0 squared, it's also equal to 0. And fxy always equals minus 4. So our d value is going to be 0 times 0 minus a minus 4 squared. All right, be careful with your negatives here. So this comes out to be negative 16. So therefore, we have a saddle point. And we stop for that critical point right there. We don't have to go any further. Once d is negative, we're done with that critical point. Now let's go to the second one, which is 1, 1. Okay, for 1, 1, fx is going to be 12 times x squared, 12 times 1 squared. It's going to be 12. Fyy is going to be 12y squared, 12 times 1 squared, also equal to 12. Fxy always equals, in this case, negative 4. So our d then, in this case, is 12 times 12 minus a negative 4 squared. So that's 144 minus 16, and I think that's 128. But all we really have to be worried about is whether it's bigger than 0 or not. So if d is bigger than 0, so we need to look at fxx. All right. In this case, our fxx is equal to 12. That's bigger than 0. It's positive, so I like to draw my positive face there, and that tells me we have a local min at 1, 1. Then I only have one more critical point, negative 1, negative 1. And in this case, my fxx now is, let's see, 12 x squared, so 12 times minus 1 squared is also 12. Fyy, 12 times, minus 1 squared is going to be 12 again. Fxy, always in this case, is negative 4. So our d is 12 times 12 minus a minus 4 squared, and that's also 128. Bigger than 0, we look at fxx value. Now this time around for this one, it's also fxx again is equal to 12, bigger than 0. So again, we have the positive face case, and we have another local min at negative 1, negative 1. All right. And then I did do it this time. If we plug in, so we have two local mins at 1, 1 and minus 1, minus 1. Notice right in between those, if you look here on I didn't graph this thing, but one of them is here at minus 1, minus 1. The other one is here at 1, 1. And right directly in between them, we have our saddle point. Okay. But anyway, the values are the function values back to the original function. If I plug in 1, 1, I get negative 1. And I also get the same thing if I plug in minus 1, minus 1. I also get a negative 1 for my function value. So these are my local minimum values. Okay. Going back to the original function and plug those in. Okay. All right. Question on that one. I said the tricky part can be you doing the algebra to get the critical points. The rest of it is pretty much mechanical. Okay. All right. Now, let's get started on this next part. There's a second part here to this section, and this involves absolute maximums and minimums. Now, what we're meaning by this is looking at the entire domain of the function. Where does it have its, if we're looking at a certain area, where does it have its biggest value? Where does it have its smallest value? Okay, I'm going to go back to a function of one variable again. All right. Now, we have this fact from a function of one variable. It's actually the extreme value theorem. Extreme value theorem. And it should have been covered as part of Calc 1. All right. So this is the deal here with this. If our function is continuous, if f of x is continuous, so it doesn't leave, you can draw it without leaving the paper, on a closed interval, that's the key here, on a closed interval, a to b, that means we include the two endpoints in the interval. Then, f of x has an absolute minimum value, absolute min value, and an absolute max value on that interval, on that closed interval. And what we mean is if there is somewhere on some value of x on that interval where we have the biggest value in that interval for the function and some other point where we have the smallest value on that interval. We're not talking about all throughout the whole domain of f of x. We're just looking at, on this interval, a to b, there's a place where the function has, so here's my function. There's going to be a place like right here where it has its smallest value and like right here where it has its biggest value, okay? Now, what you found in first semester calculus was this. These absolute min and absolute max values, these absolute min, let me put slash max values, will occur either, oh, I should have put an either here, either at the two endpoints or at a critical point inside the interval from A to B. So you're only going to look for these biggest and smallest values at a few places. You're going to check the two endpoints, and then you're going to also have to look at critical points that are inside, for x values that are inside the interval. Now, we have a similar finding for functions of two variables. So, before we go into what it is, I need to introduce just some notation here, or a definition. A closed, bounded set in the xy plane contains all its boundary points and does not extend to infinity in any direction, and does not extend to infinity. This is believe me, a very loosey-goosey definition, but I think it gets the point across, and does not extend to infinity in any direction. All right. So examples would be a circle this is on the XY plane that includes all of the circumference of the circle. All right, that's a closed bounded set. Another example would be, say, a rectangle on the XY plane that includes all of the sides of the rectangle. Or we could have a triangle in the XY plane that includes all the points on the three sides. Those are all examples. Now here's examples where it's bounded but not closed. Closed means it includes all of the boundary points. So we could have a circle where this part of the circle is not, that part of the boundary of the circle is not included in our set for whatever reason. It's bounded, it doesn't go to infinity, but it's not a closed set because we have some of the boundary missing, so to speak. Same thing with the rectangle, we can say have those two sides, but for whatever reason we're wanting to exclude the other two sides. Again, it's not a closed set. Same thing for a triangle. We can include one of the sides, but say not include the other two sides, and again, it's not a closed set. So what's the deal? Why do we demand that it be closed and bounded? Well, if our set in XY is closed and bounded, then our function that's defined on that will have an absolute biggest value and an absolute smallest value on that set of XYs, right? So that's the corresponding theorem for this. So extreme, so we'd call this the extreme value theorem for fxy, two variables. Okay, so here it is. The function has to be continuous, so fxy, if it's continuous, now it has to be on a closed, bounded set. We'll call it capital D. This is not the same capital D as we talked about a few minutes ago. Then f of xy attains an absolute max and absolute min value in the set D. Okay, so we'll have a biggest value for xy's on in that set and a smallest value. Now the technique, how do we kind of do this? Because you would be asked, well, tell me, what is the biggest value of the function? What's the smallest value? This is what you have to do. You first of all have to find the critical points on the inside of whatever your capital D is that you're given. And then you find the function values for those critical points. In other words, you plug the critical points into your original function. Plug the critical points into your original function. Okay. And then you also, these biggest and smallest values could occur on the boundary also. So now you have to find the biggest and smallest values of the function along the boundary. And this can be a little bit of the difficulty with this process. So find the largest and smallest values of the original function fxy along the boundary of our set. And then our last step, if we've made it this far, our last step is very simple-minded. We compare all these function values that we got. We compare the values we got at the critical points inside the set. We look at the function values we got along the boundary, and it amounts to the biggest value we came up with. That's the absolute maximum value. The smallest function value we found is the absolute minimum function value on that set. So, number 4 is we compare values in steps 2 and 3. And the largest value is the absolute max value, and the smallest value is the absolute min value. All right. Okay. I'm just going to introduce the thing that we'll be talking about on Friday. There is no way we can complete the problem in 10 minutes. Maybe I could, but well, gee, what's the point? Okay. Let me just introduce it and we'll look at, so what we're going to talk about on Friday after you guys do the quiz is this function, x squared plus y squared minus 2x, all right? And what we're going to do in our region D is going to will be a triangular region, and with the 3 vertices, what do we have? 2, 0, I'll draw it in just a second, 0, 2, and 0, minus 2. So this is what the area is that we're looking at function values. Okay. All right. So the 3 vertices, 2, 0, so 1, 2. So here's 2, 0. The other one is what? 0, 2. Right here, and the third one is 0, minus 2. Right here. So here's our 3 vertices. So let's connect them with straight lines. So this is our triangle, and that's our region D. And what we're going to look at, so this is our y and this is our x. We're going to try to find the absolute max and min values of our function over this set D. And it will have a biggest and a smallest value, all right? So we're going to look at critical points, and then we're going to find out there's going to be one single critical point right on the inside of the triangle. We're going to then have to look along each of these 3 lines, because we have 3 lines on the border. I'm going to be calling this line L1, this line L2, and this third line L3. And we're going to have to look at what the function values are along those 3 lines. And then we compare everything and see what is the biggest value of the function and what's the smallest value of the function. What's going to take the time is going along these lines and figuring that out. The critical point is not going to take any time at all. All right. All right. So that's no need to go further with this right now. So we'll just continue with this on Friday.